Okay, so now that you understand what the Cartesian product of two sets basically is, now we can move on to relations. And basically a relation is, well, I will explain what a relation is. So a relation, so you have basically considered considers, for example, two sets. For example, P is this set A, B, and C. And we have another set, for example, Q, which contains these names, right? Like Ali and Bahanu and Binoy and Chandra and Divya. These are the two sets that we have. Now the Cartesian product of P and Q, since n of P is equal to 3 and n of Q is equal to 5, then the Cartesian product of P and Q has 3 times 5, which is equal to 15 elements. Which has basically the elements of P, and the Cartesian product of P and Q would be basically, for example, A comma Ali, for example. You have A comma, for example, Bahanu. A comma Bahanu. You have A comma, for example, Binoy. Right? You have A comma Binoy. And it just keeps going all the way up to C comma Divya. C comma Divya. So this would be 15 elements. Now, basically, considering all of these 15 elements, we can now obtain a subset of P times Q we can now obtain a subset of P times Q, and you need to pay attention to these words. A subset of P times Q. By introducing a relation R, by introducing a relation R between the first element X, between the first element X and the second element Y, and the second element Y of each ordered pair X comma Y, as, so if I take all of these elements as X and Y, and so on and so forth, now we can now obtain a subset of P by Q, a subset of this set, and of course you can imagine that the subset of a set could be the set itself, meaning that the subset of P times Q could be, for example, could be this set over here, for example, set A, for example, which contains only this element here, A comma Ali, or you can say that basically a subset of the set P times Q could be the whole set itself. That is also a subset of P times Q, right? So we can now obtain a subset of P times Q by introducing a relation R between the first element X and the second element Y of each ordered pair X and Y. And so that relation is basically a rule that we can basically define here. For example, I say that basically the relation R is such that, for example, the first element the first element in each case is also the first letter of the name in the second element. For example, this would then be a candidate there, because A and A would match together. But A and B would not match together. A and B would not match together, and so on and so forth. So now what I can do is that I can say that, for example, in that exact situation that we had over there, which we had basically the sets P as basically A, B, and C, and the set Q we had it as those names as, for example, Ali, Bahanu, and we had Binoy, and we had Chandra, and we had Divya, right? So now you know that basically the Cartesian product of these two sets is going to be some set that contains 15 elements. Now in this situation, I can obtain a subset of P and Q by introducing a relation between the first element and the second element of this set X and Y. Right? If I imagine that each element in this set is some ordered pair X and Y, then if I introduce a relation between X and Y, based on that relation I can basically obtain a subset of P times Q, right? And I can define that relation in any way that I want, or in any way that I need. Meaning that I can say that relation is going to be all the ordered pairs X and Y, such that X, for example, is the first letter of the name. Y is the first letter of the name Y, and X belongs to, for example, the set P, and Y belongs to the set Q. That is the relation that I define here. Now, based on that, then I can write the set R as this is in set builder form. In raster form, I can write that as, for example, A goes only with Ali, A and Ali. And then B goes only with Bahanu and Binoy. B goes with Bahanu, and B goes with Binoy. And then C goes only with Chandra. C goes only with Chandra. And you can see that in all of these cases, these letters are also the first letters of the names: AA, BB, BB, CC, and basically Divya is just simply not there because we have no D there. And so a visual representation of this relation R, a visual representation representation of R called an arrow diagram, would be, for example, this set over here, would be this diagram over here. Suppose that I have A, B, and C, and this is the set A, the set P. This is the set P, and I have another set Q, which is basically all of these names as Ali, and I have Bahanu, and I have basically Binoy, and I have Chandra, and also I have Divya. And then that would be the set Q. Now this relation from P to Q would be represented by this arrow diagram with A to A, from A to A, from A to Ali, B to Bahanu, B to Binoy, and C to Chandra. Right? That is a visual representation of that relation that we defined in that particular case. Now, so based on this situation, now we can define a couple of things. We have basically 3 definitions here. So definition number 2. Okay, so definition number 2. So definition number 2. Definition number 2 is basically a relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product of A and B. Now the subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A times B. The second element is called the image of the first element. So a relation R, a relation R from a non-empty set A, from a non-empty set A to a non-empty set B is a subset of the Cartesian product A times B. Is a subset of the Cartesian product A times B, or the Cartesian product of A and B. The subset is derived by describing a relationship between the first element and the second element of the ordered pairs of the ordered pairs in A times B. So basically the subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A times B. The second element is called the image of the first element. So this was definition number 2, and definition number 3 is basically the set of all first elements of the ordered pairs. The set of all first elements of the ordered pairs in a relation R in a relation R from a set A to a set B, from a set A to a set B, is called the domain of the relation R. It's called the domain of the relation R. So what this definition means, so first of all, let's go back to this definition here, which is saying that basically a relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product of basically A and B. The subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A times B. And the second element is called the image of the first element. So you can see that over here. So we have a relation from, let's say, A to B. Let's take this as set A, and let's take this as set B. And a relation from A to B, here basically we define that relation as the rule that basically the element in the set A was supposed to be the first letter of the name in set B. So we said that the relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product of the set A times B. So the Cartesian product of these two sets would of course contain all of these elements over here, meaning that you would have A2, meaning that you would have this, all of these over here, right? You would have all of these, you would have all of these, you would have all of these, and then you would have also all of these. All of these basically, all of these relationships. But now, and you can see that basically 3 times, for example, 5 is equal to 15. And if you actually count these lines going from each of these elements to each and every one of these elements, you will find exactly 15 lines going from this set to this set, except for the ones that I drew earlier, right? So what that means is that What that means is that basically I have a non-empty set A here, and I have a non-empty set B here, and basically a relation R, if I call the rule that I defined here as a relation R, that from a non-empty set A to a non-empty set B is a subset of the Cartesian product of A times B, meaning that I'm not considering all of these relations, A with Ali, A with Bahanu, A with Binoy, A with Chandra, A with Divya, and so on and so forth. I'm not considering all of them, I'm just considering a subset of them, only some of them, or possibly even all of them, but not necessarily all of them. And the subset is derived by describing a relationship between the first element and the second element. In this case, we said that, for example, this element here is supposed to be the first element, the first letter of these names, right? So the subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A times B, and the second element is called the image of the first element. So in case I have basically all of these elements figured out here, so what I can do is that I can, let me draw this again. So I can say that, for example, this is A, and this is B, and this is C, right? And this goes to, for example, based on the rule that we defined earlier, we said that basically A goes to, for example, this one, and A goes to nothing more, B goes to this one, and also to this one, and C goes to this one, right? So then we said that basically the second element is called the image of the first element. That means that you can, over here, you can say that Ali is the image of A. Ali is the image of A, is the image of A under the relation R. You can also say that, for example, Bahanu is the image of B under, again, the relation R, and so on and so forth. Now, the second definition that we had here was that, which was definition number 3, we said that the set of all first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation. Meaning that the domain of this relation is, in this case, is basically the domain, if I call this relation, basically if I call it R, the domain of the relation R is basically equal to this set which contains A, B, and C, which is incidentally also equal to the set P as well, right? But sometimes it's not necessarily the whole set. Sometimes it's a subset of the set P. So that was definition number 3. Now definition number 4. Definition number 4 is basically the set of all second elements in a relation R. The set of all second elements in a set R, the set of all second elements in a relation R, actually, in a relation R from a set A to a set B, from a set A to a set B, is called the range of the relation R. It's called the range of the of the relation R. And so that is about the range, and the whole set B, and basically the whole set B is called the codomain of the relation R. It's called the codomain of the relation R. And note that basically the range, so this is the codomain, and you can see that as basically note that the range is a subset of the codomain. And so you can see that basically we say that basically the set of all second elements in a relation R from a set A to a set B is called the range of the relation R, basically. So the set of all second elements would be the range of this relation R. So that means that here I can say that the range of the relation R is equal to this set which contains only these four elements, which is basically Ali, Bahanu, and Binoy, and Chandra, right? And that is basically your range. And then here we said that basically the whole set B is called the codomain of the relation R. So the codomain of the relation, the codomain of R is equal to basically all of these elements, which is equal to Ali, Bahanu, and Binoy, and Chandra, and Divya. And as you can see, this is actually equal to the whole set Q. And also you can see that the range is actually a subset of the codomain. Now, and of course you can imagine that the range can be equal to the subset, meaning that they could be equal sets, meaning that the range and the codomain could be actually the same things, the exact same sets or equal sets, provided that all of the elements over here are elements of the range. If some elements are not elements of the range, then the range is going to be a proper subset of the codomain. A proper subset means that there is basically two things in sets that we didn't discuss in the course related to sets, but there is something called a proper subset of a set. A proper subset of a set A is a subset of A that is not equal to A. In other words, if B is a proper subset of A, then all elements of B are in A, but A contains at least one element that is not in B. So mathinsight.com, there is also the concept of a proper superset. So a proper subset means that now there is one more way to, and there is basically there is one more thing that we have here: a superset, a subset, proper or strict subset is a subset or a strict superset of A. Now there is something else that I don't really remember right now. But then when you say that, for example, see that the point here is that there is this term called the proper subset. And what that means is that when I say that, for example, let's say that A is equal to 1, 2, 3, and B is equal to basically 1, 2, 3, and 4. Now in this case, I can say that A is a proper subset of B. Now I'm not using any math notation because there is two notations here. There is this notation and there is this notation. One of them means proper subset, one of them means just subset, I suppose. Now, I'm not really sure about that. Meaning that I think this notation means that they could be also equal sets, meaning that this might actually refer to the concept of subset, and this means proper subset. But you do need to look this up. I'm not really sure about this. Okay. Now, but what I do know is that basically in this particular exact case, you can say that A is a proper subset of B because it's a proper subset of B because basically A and B are not the same sets, they are not equal sets. But then in this case, for example, if A is equal to 1, 2, 3, and 4, and if B is equal to basically 1, 2, 3, and 4, and well, of course, you can say that A and B are equal sets, and you can say that A is a subset of B or B is a subset of A, because any set can be the subset of itself. Now you cannot, in this case, you cannot call this A a proper subset of B because A is equal to B and B is equal to A, or you cannot say that B is a proper subset of A. So now based on this concept and based on this definition, what we can say is that you can see that over here we said that the range is basically the set of all elements in the relation that have been mapped from the domain. That means that basically the range over here is Ali, Bhanu, Binoy, and Chandra, and only these 4 elements. And since this element is not a part of the relation, therefore it's not a part of the range. On the other hand, we have the idea of the codomain, which is simply the whole set that is basically, that mapping is basically done to. So the mapping is done to this set over here, the second set. So the whole elements of that set is basically a part of the codomain of the relation. And as you can see, the range is a subset of the codomain. And if your relation happens to include all of the elements of the set Q, then of course the range and the codomain are going to be equal sets, right? So that's basically the range and the codomain. So now we know about the domain. So the domain is basically this part over here. These elements are your domain. These elements over here are your range. And these elements over here, all of these elements are your codomain, right? Domain, range, and codomain, right? Now as a next point here, as a remark, we can say that basically, remark number 1, we can say that a relation may be represented algebraically either by the raster method or by the set builder method, which is pretty obvious. So the relation could be represented by, for example, R is equal to all the ordered pairs x and y, such that, for example, this relationship exists between x and y, and so on and so forth, and all of these relations, and that is basically the set builder form. On the other hand, the same relation can be represented in basically raster form, meaning that x1, x2, x2, x1, y1, x2, x2, y2, and all the way up to x of n, y of n. This is in raster form. So basically, a relation may be represented algebraically either by raster method or by the set builder method. And remark number 2 is an arrow diagram is a visual representation of the relation. So this is an algebraic representation of the relation, either of these two ways. And basically the arrow diagram is a visual representation of the relation that we have, which is pretty simple to understand. Now let's do a couple of examples here. Let's do a couple of examples and see what we have here. Okay, so now let's do example number 7, which is, let's say that we have some set A which is equal to basically 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And you want to define a relation from A to A. You want to define a relation from A to A by R is equal to all the ordered pairs x and y, such that y is equal to x plus 1. And number 1, you want to depict this relation using an arrow diagram. And also you want to write down the domain, codomain, and range. You want to write down the domain, codomain, and range of R. Okay. Now, first of all, basically R would be, as you know, R is a subset of the Cartesian product of A and A, meaning that if you have the set A here, which contains all of these elements here, and again, if you consider the same set A, now basically over here you have, for example, you have all of these elements and all of these elements, and then you can write the Cartesian product of A and A, you would consider this element with this element, and then this element with this element, this element with this element, and so on and so forth. And then you would start with this element again with all of these elements, consider this element again with all of those elements, and consider this element again with all, and so on and so forth. And then in that process you will get all of these basically elements x and y. I denote them as x1, for example, y1, and x2, y2, and all the way up to x of n, y of n, right? So then x1, and in this set, basically x1 belongs to x1, and you can say that basically x1, x2, all the way up to x of n belong to basically the set, to the set, of course they belong to the set A, and y1 and y2 and all the way up to y of n also belong to the set A, right? So that is basically a relation from A to A. Now, that is the Cartesian product of the set A and A. Now, a relation R would be a subset of this set based on some rule, meaning that I'm saying here that R is basically all of such ordered pairs x and y such that y is equal to x plus 1. Now, if R is supposed to be x plus 1, what that means is that if I write my A as the set A as, for example, 1, 2, 3, 4, 5, and 6, right? So, and then as a result I would get 1, 1, 1, 2, 1, 3, all the way up to 1, 6, and 2, 1, 2, 2, 2, 3, all the way up to 2, 6, and so on and so forth, all the way up to 6, 6. Then basically R would be a relation which is a subset of this set. Now, the subset of this set, and the only condition that I have here is that y has to be x plus 1, meaning that the second element here, this element, has to be basically 1 more than x. 1 more than x. Now, 1 comma, for example, if I consider 1, 1, that would not satisfy this condition. 1, 2 would satisfy this condition. And 1, 3 would not. 1, 4, 1, 5, 1, 6 would not. Then could 2, 1, if I write basically 2, 1, we said that y has to be 1 more than, y has to be equal to x plus 1, right? So x plus 1 would be 2 plus 1 is equal to 3, which is not equal to 1. So this is not basically what I'm looking for. If I write 2, 3, then x plus 1 is equal to 3, and basically y is equal to 3. These are equal, so this is what I'm looking for. This is 2, 3. And then by the same logic, you can go for 3, 4, and 4, 5, and 5, 6, and there is no more elements here that you can write. So among all of those, basically, you would get basically in the Cartesian product of A and A, you would get 36 elements. Among all of those 36 elements, these are the only elements that you could characterize as belonging to the set R, or the relation R, based on the rule that R is equal to the ordered pairs x and y such that y is equal to x plus 1, right? Now, now that we have basically our relation here, everything worked out, so now we can depict this. Now we can depict this basically using an arrow diagram. So I have 1, 2, 3, 4, 5, and 6. That is the set A. And to just be consistent with the arrow diagrams in the book, I basically do these bullet points. So 1, 2, 3. So 1, 2, 3, 4, 5, and 6. And then this is again set A. And this is a Cartesian product. This is a relation from A to A. So I have to put my set A over here. So I have 1 to 2. I have 2 to 3. I have 3 to 4. I'm sorry, I had to okay. So I had basically 1 to 2, which is basically this arrow over here. I have 2 to 3, which is this arrow over here. 3 to 4, which is this arrow over here. I have 4 to 5, which is this arrow over here. And I have 5 to 6. Right? So as you can see, this element is not a part of our relation. And this element is not a part of our relation either. And this is basically a visual representation of our relation using an arrow diagram. Now if I want to write the range of R, so we have 3 things over here that we want to write down. The range, the codomain, and the domain. Now the domain of R is a set. Is a set of elements, which is basically all of the elements that are a part of the relation, that basically take part in the relation and are elements of the set A, or you could say the first set. I can call this the first set. This is just some loose way of talking about things, but just to have a way to talk about the sets, I would call this the first set, and this is the second set, right? Now, the domain is basically all of these elements 1, 2, 3, 4, and 5, and not 6. Because 6 has not been mapped to anything here. The range of R is basically all of these elements that have been mapped to 2, 3, 4, 5, and 6. And the codomain of R is basically all of the elements of A, even the elements that have not been mapped to. Meaning that you have 1, 2, 3, 4, 5, and 6, which is actually equal to the set A. So then you can say that the domain is 1, 2, 3, 4, 5. The range is 1, 2, 3, 4, 5, 6. And the codomain is 1, 2, 3, 4, 5, and 6. Now this is something that you need to understand. This is this situation, this exact situation that we talked about here. This is something that you need to understand properly. You can make a screenshot here if you need to. And also make a screenshot here if you need to. And this is the kind of situation that you need to, or you can probably rewind the video or whatever it is that you want to do. But this is the type of situation that you need to understand. Because if you don't understand this, you will not be able to understand functions. If you don't understand functions, well, simply you can say that you cannot understand mathematics, because everything is in mathematics except for the very simple things. For example, except for arithmetic, everything else that we know that we call mathematics is just simply functions. And then if you don't understand functions, you will not be able to understand calculus. If you don't understand calculus, you will not be able to understand any branches of science. So I suppose it's the one of the most important concepts in mathematics is just this simple situation which needs to be understood, which is of course not complicated at all, but it needs to be understood properly. But of course we have a couple more examples here. If you pay attention to the way that I solve these problems, you will of course understand them. Now, even if you happen to have some doubts here, that's not a problem, not at least for now. Now, the next question is question number 8, and these questions are all important. These need to be done so that we can move on to the next concepts. Okay, so let's do another example here. Let's say that the figure 2.6 shows a relation between basically the sets P and Q, right? This relation in set builder form and raster form, what's the domain and range? So we have basically these elements 9 and 4, and we have also 25, and this set is called P, and we have another set 5, 3, 2, 1, 5, 3, 2, 1, -2, -3, and -5. And you have basically these elements here as well. And these elements constitute a set called Q. Now, in this situation, 9 has been mapped to 3 and -3. 4 has been mapped to 2 and -2. And also 25 has been mapped to, and 25 has been mapped to 5 and -5. Right? That's the situation that we have. You want to write this relation in set builder form. In set builder form, if I call the relation R, for example, I could say that R is equal to, so let's first write them in raster form. In raster form, basically the relation R could be basically 9 to 9, 3, and 9, -3, and 4, -2, and 4, 2, and 25, -5, -5, and 25, 5. Right? So that is the set that I have, and that is the relation R. And I can say that basically X is always X is always the square of Y. As you can see, basically 3 squared is 9, -3 squared is 9, -2 squared is 4, 2 squared is 4, and so on and so forth. So you can say that X is always the square of Y. So I can write here in set builder form, I can write all the basically ordered pairs X and Y such that X is the square of Y. X is the square of Y, and basically X belongs to the set, for example, P, and Y belongs to the set Q. That is in set builder form, that is in raster form. And the domain of this the domain of this relation R, the domain of R is equal to this set that contains all of the elements that have been mapped to the elements in the codomain or in the range, meaning that you have basically 4, 9, and 25, all of the elements here. This is your domain. Your range is basically all of the elements that have been mapped to, which is 5, 3, 2, -2, -3, -5. So you have -5, -3, -2, and 2, and 3, and 5. And your codomain is basically all of these elements that you can see over here. So you have -5, -3, -2, and 1, and 2, and 3, and 5, which is incidentally also equal to the Q, right? And of course you can see that this element here is not related to any element in the set P. In the set P, it's not related to any of the elements here. So, meaning that it's not been mapped to in any way, but all of the other elements have been mapped to. And the set Q is the codomain of this relation. So that's basically, for example, another example. And the total number of relations that can be defined from a set A to a set B is the number of possible subsets of A times B. So this is also some interesting note, and that is basically the total number of relations. And you know what I mean by relation, meaning that basically, first of all, you have this set P and Q. The Cartesian product of P and Q would contain basically 1, 2, 3, 4, 5, 6, and 7. 3 times 7 is equal to 21. So 21 elements, or 21 pairs, right? Now these 21 pairs, in this case, basically, if n of P is equal to, for example, 3 and n of Q is equal to 7, then n of P times Q, which is the number of the elements that you find in the Cartesian product of P and Q, is 3 times 7, which is equal to 21, right? So 21 elements you have in there. Now the number of the subsets of this set, then the total possible number of subsets of this set is going to be equal to the total number of the elements of the superset of this set, right? And we talked about this before, meaning that, or to make it simpler, you can say that the total number of subsets of P times Q is simply equal to 2 raised to the power n of P times Q. N of P times Q. Meaning that if I take n of P times Q as, for example, some number P, for example, then basically this would be equal to 2 raised to the power P, right? And of course this P is a lowercase p. I will write it this way so that you recognize that this is a lowercase p. So, and this is also a lowercase p. So from now on, I'm going to write my p's as this is an uppercase p, and this is a lowercase p, to distinguish between the two. Now, so now basically over here, what the total number of subsets of this, the total number of subsets of the Cartesian product of these two sets P and Q is going to be equal to, so in this particular case, the total number of subsets is equal to 2 raised to the power 21, right? Which is incidentally also equal to the total number of relations that can be defined on the Cartesian product of the two sets. Because you have the Cartesian product of the two sets, you define some relation on that Cartesian product, and based on that you will get some relation. Now these relations are nothing but a subset of P times Q, right? And for the same reason, the total possible number of subsets of P times Q is also equal to the total number of possible relations that you can define on P times Q. And so based on this situation, you can say that the total number of relations that can be defined from a set A to a set B is the number of possible subsets of A times B, which means that if n of A, let me write this down, I want you to understand this. So you can say that the total number of subsets, the total number of relations, the total number of relations that can be defined from a set A to a set B, from a set A to a set B, is the number of possible subsets of the Cartesian product of A and B, right? So we understand what that means. Now if n of A is equal to basically P, let's say, and n of B is equal to some constant Q, then n of A times B is equal to, of course, P times Q. And the total number of relations would therefore be 2 raised to the power P times Q. 2 raised to the power P times Q. Right? So that is that. Now, let me do another. Well, we don't really need to there is another example, number 9. If it's important, we will do it in the next video, and the next video we will also talk about exercise 2.2 a little bit as well. So I'll see you in the next video, and thank you.